Hello, 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 ladies and gentlemen, and welcome back. We are going to finish off our look at the 2006 Cayley paper because we are on question number 25. Hopefully you've given this one a bit of a try yourself, and let's take a look at it. A semicircle of radius 8 centimeters rocks back and forth along a line. Okay. The distance between the line on which the semicircle sits and the line above, this line up here, is 12 centimeters. So that's a parallel line, okay. As it rocks without slipping, the semicircle touches the line above at 2 points. When the semicircle has hit the line above, it immediately rocks back in the other direction. I don't see why... I guess to get the 2 points, you could read that so that it only hits 1 point, maybe. The distance between these 2 points in millimeters is closest to. Okay, so things to note, they have millimeters, but they've given everything in centimeters, so I'm betting that these 2 points are quite close to one another. And also, it's not going to be as obvious as... so we've got this guy. What do they call it? The semicircle. It rocks back and forth. It doesn't stay right here as it rocks, so it's not going to rock up like this. I know it says not slipping, but the question is not going to be as simple, I don't think, as just completing the circle and then counting the distance between these 2 points. No, what happens is so it starts here, and then as it rocks, the point that it touches at moves. It doesn't slip and slide, so it goes in a very predictable way. So from this point up has now sort of flattened out to become the distance from our original starting point. Okay, and that's the new touching point. So, what does this look like when I'm at one of those peaks? So I've started my bowl, it's not a bowl, it's a semicircle. I'm probably going to keep calling it a bowl because in my head it's a bowl rocking back and forth. And that's fine if I want to view it that way. I want to make sure that my semicircle is actually touching here. We'll draw the semicircle first and then draw the line. Alright, so what does it look like when it's touching? Well, when it's touching up here, well, first of all, it's not going to quite be up there, I don't think. It's going to be... So it'll be somewhere up here. It touches, and then the bowl sort of now looks a little something like this. Not perfectly to scale, but it's not terrible. Okay, so as I said, the way that this thing is rocking, this new point of contact here, which I think is probably going to be quite crucial, and this point of contact here, the distance between the two of them is the same as the distance that you need to go from that point around the semicircle to the point of contact when the bowl is resting. Okay. So that's fine. Now, we know the height here, and I don't quite know where I want the height. Either it's going to be here, which I don't think is particularly useful, or right here. We know the height is 12 centimeters. And the radius was 8, so this fellow right here is 16 centimeters. So I do have a triangle. I've got a sort of a right angle triangle here. And of course I could extend this guy to be another right angle triangle. So there's definitely some right angle triangles going on here. I just don't quite know what exactly it is that we want here. Now, if I've got a right angle triangle, with whose hypotenuse is the diameter of a semicircle, this guy actually has to be on the semicircle. Yeah, he has to lie on the semicircle. So that's a useful piece of information, probably. That's a nice circle geometry result. Okay. And I think if I can figure out how far away this point is horizontally from our starting point, by symmetry it's going to be the same thing. And I can take the difference of those two, I guess. So, having trouble deciding where exactly to go. I suppose this distance here might be important. And so if I called that, say, H, then this is going to be 12 minus H. And this can be determined in terms of H. Does that actually help me? Not especially. So, gosh, I feel stuck right now. I feel like there's just not enough information yet in my picture to start doing something. (16 and 12) keeps sort of jumping out in my head that it's 16 and 12 are part of a Pythagorean triangle, but not with 16 as the hypotenuse, so that's not helping. In fact, is 16 ever the hypotenuse? No, it couldn't be. So that's pesky. What to do? I've got right angle triangle here. There wasn't any other piece of information, is there? Rocks without slipping, semicircle touches the line above at 2 points. And it's in millimeters, so it's going to be, 53 millimeters is about 5 centimeters, so maybe it's not unreasonable that we see this. I think I'm going to redraw my picture. I think I need a fresh perspective. So we get to this intersection point. here, this point of tangency. And it is a point of tangency, so we're going to have, if I connect it up to the center, it's got to be a right angle. Haha. A right angle of height, the radius, which is 8. And then we've got this 8 here. And, well, that right angle isn't going to really be going anywhere. I definitely like that I've now seen this. Now the question is, what else can I do? The only other thing I can think of is draw our initial sort of base point. Because he makes those, so he's the one that when it was originally sitting like this. That's our original starting point. How far has that moved? If I could figure out maybe this slice here, I'd be all set. With an 8 there, I guess with a height of 12, we've got a 4 here and a 4 here. So doubling that, this is going to have to be 4, so it's a 16, 8. Oh, it's a 30, 60, 90 triangle. So this distance is 8 root 3. Here we go. I think we've cracked it. So 8 root 3 is how far? That is. This is a side length 8. And in terms of where this guy is, so make a right angle there. I think I'm quite close. I like that I've seen that. I don't have to be writing this or proving this, so that's nice. I can just work off my picture until I get a calculation I want to make. By the way, knowing that we've got a 4 and an 8, if you've got a 1 to 2 ratio between a side and the hypotenuse, the other one has a ratio of root 3, and you have angles of 30 degrees, 60 degrees, and 90 degrees. It's quite helpful. And you see how I got this 4 over here? It's because this one is also perpendicular. Going to have to lie on the same line because he's a smaller version of this bigger triangle involving the hypotenuse. Okay. So now, I think I want to bring back my so this distance in here is 4 root 3. So now this point right here, can I calculate where he is exactly? He is distance 8, so this guy's got to be 4. Because I know whatever the distance from my immediate sort of center to this new point of tangency, whatever that is, as an arc length, I take that, I subtract off this 4 root 3, and that's the distance from this guy over to the line that I'm interested in, the line that gives me the apex here. So now, if I've flipped over my semicircle, I've got the 8 here. This is I'm going to use the red for my original point of contact. Okay, so now if I connect him up, we get a bunch of 45s. And then this one here has a 60 and a 30, so he's actually further over here. That's where this point is. Now, these two lines are parallel, so this is 60 degrees here. So it's a right angle here, and it's 60 degrees here, so they're 30 degrees away. It's 30 degrees for this point of contact. Okay. So if they're 30 degrees, so the distance from the original point of contact to new point of contact is equal to a 30-degree arc of the circle, well, the semicircle. So how do we, well, the radius is 2 pi r, and if you want a 30-degree arc, you do a fraction, 30 degrees over the full 360 degrees, 2 pi r. And this becomes 1/12 2 pi r, and r is 8, so this is 16 over 12 pi, or 4/3 pi. And then we come back by 4√3. So distance from original point of contact to a line perpendicular to the baseline from the apex, from the point where the semicircle reaches up and touches the other line, is 4/3 pi minus 4√3. So, whoops, I tabbed when I wanted to go back. Okay. So we care about. Actually, let's redraw, and I'll explain it for people who weren't following my diagram. Okay. So our bowl starts off like this, or our semicircle starts off like this, and we have this point of contact. And as the bowl tilts, it rolls a bit, and then eventually it looks a little something like this, with a brand new point of contact. So our original point of contact moved here, and we've got this point of contact here, which was originally here, and so this distance here is what we've calculated, the 4/3 pi. Okay? Now, we care about how far over this apex is, because when it rolls the other way, we'll get a mirror image, the exact same thing but in the other direction, and we want to measure this distance between the two. So what I'm really doing is measuring their distance between this central point here. I'm just going to double that length, whatever it is. Okay. Now it doesn't actually matter if the picture looks like this, or if the bowl's apexes look sort of like this, which I think is probably more accurate. Okay, it doesn't actually, if we sort of roll to the right, it doesn't actually matter if the apex is on the left or right, because I just want this distance here, and I'm going to double it for the other one as well. Okay. So if this, I think this is going to turn out to be negative, doesn't matter, I'm just going to take the absolute value and maximize. Anyways, how did we get this? Well, we use purple here. This guy here, this apex line is a right angle, because it's straight up off of this line here. And this one also is straight up off this line, but I know that hits the center. We get 8 here. And then we get 8 here, but we know in total we've got 12, so this is 4, 4, 8, 12, and this has got to be a right angle. So not only does the distance here become 4 root 3 by Pythagoras or knowing the 1 root 3, 2 triangle, but we're also able to make this calculation because this is going to be 60 degrees here, and this is going to be a right angle. And that gives us a 30-degree distance for this arc. Okay. So whatever this is, so the distance, I guess I've got to absolute value it. So distance between the two apexes, or apices, I believe is the proper term, is going to just be twice this distance. And this is where we brought our calculator. I mean, I know that oftentimes with the early questions on Pascal, Cayley in this case, a Fermat, you'll get things like what was the first question for this one? It was, a half plus half times a half. That's the first question. Second question, the first couple are all just calculations. I know that you can say to yourself, well, gee, I can do all those early ones, mental arithmetic, just fine. If I don't remember my calculator, no big deal. But with this question right here, with question 25, what have we got? We've got a closest to question. We need to use our calculator, really. Maybe, just maybe you can, pi about 3.14, root 3 about 1.73. Maybe you can approximate. But you're going to need at least 2 significant digits there. Probably 3 would be better to discern between each of these. Because remember, these are in centimeters, whereas our answers are in millimeters. So it's really 5.3 centimeters, 5.1 centimeters. So you've got to be very careful. So now 4 over 3 times pi, 4.188, minus 4 times root 3. It is negative. It's negative 2.73. So this is 2 times the absolute value of negative 2.73. So it's going to be 2 times 2.739. So we'll multiply that by 2, and we get 5.478826. And that is approximately 5.5 centimeters, or 55 millimeters. I do like that it's off by 2, so there's no question of rounding errors. Either you get it right or you get it wrong. If 43 had been one of the answers, somebody would have said 43 and said, well, I round down. Don't matter. I'm a little perplexed as to why they chose millimeters rather than saying closest to the nearest tenth of a centimeter is. But whatever. We've got it, and our answer is 55. It took a little while. I liked that there was the 30, 60, 90 triangle in there. Made some of the calculation pretty easy. But I think the real challenge here was getting the right picture and the right setup to get our answer. And 55 was what? It was A. So we'll finish the contest off properly, and there's our A. We would bubble in A. And hopefully we have gotten everything right. 8 marks there, 8 marks for the previous Part C questions, and hopefully we got 150 marks in total. So that's the 2006 Cayley, all done, all squared away. The next Cayley will be the 2007. I'll be going on to do the 2006 Galois, which is still aimed at the 10th grade level. It's just written. But if you're looking for more multiple choice questions, the next one I'm going to be doing is the Fermat paper, which is grade 11. So a little harder. Maybe you'll get lost on the Part Cs, or maybe you're looking for a challenge. But those are the contests I've got coming up, and the 2007 Cayley will be at some point in the future, but a little ways from now. Okay, so thank you for watching, and whatever my next video is, I hope to see you guys there. Feel free to like or subscribe, or just share amongst your friends if you got a math circle, and you got other people who want to know answers, and you're sick of answering their questions. Direct them this way, and I'll take care of that. So, I got nothing else to say. Have yourselves a wonderful day.